Okay, welcome to biomechanics lecture. Like I always say, deadlifts are awesome, but so is biomechanics. Which leads us to the question, what are biomechanics? Well, before we talk about that, let's talk about this is a little venture I had actually to Finland. And this is the University of Jyväskylä, and that's me standing on the world's longest force plate out of Pavel Komi's lab. And Pavel Komi is known by many to be the father of biomechanics. So biomechanics is the application of mechanical principles in the study of living organisms. And one thing I want to point out is that biomechanics can enhance strength or any movement, right? So what is strength? Strength is the application of maximal force against an external object. The maximal force that can be generated at a given velocity of exercise or movement. Okay? There are several types of strength. For example, dynamic strength means you have external movement, like you're lifting a weight. And static strength would mean you have no movement, like if I took my hand and pushed it against a wall. So mechanics is cool because we can make a lot of modifications to movement. So for example, in the top right picture, that's me. I'm around 205 pounds there, and I'm squatting 405 pounds, okay? So you notice that the bar is very high in my back, and it looks very awkward. It's heavy weight, and that was extremely hard to lift. Again, I was around 205 to 210 pounds at that point. The graph below the lower right, I'm 172 pounds. So I'm over 30 pounds lighter, but I'm lifting the same weight, 405 pounds, with ease. Now, I lost 30 pounds, but I'm lifting, and I'm way less muscular, so it's not muscle that's explaining this, and I'm lifting the same weight with a lot easier. Why? I changed my mechanics. Look at the bar placement on the top and on the bottom. By shifting the bar downward, that increased my mechanical advantage. So you can see how much easier it is for me in this video here. So this is heavy squats in the lab, and I'm squatting 405.
Get it! Come on, you got it! Go! No pressure! No pressure! It's nothing, there you go! Perfect form! Got it! Push it! Up and down! Push! Get it!
So, you see that's pretty easy. Again, a lot of it's just mechanics, and that's what changed that right there. So, let's talk about some terminology on biomechanics. What is power? Well, power is work over time, right? We also say that power, if you look at work over time, you know, we can also modify that and say it's force times velocity, right? So, because essentially, work itself is force times distance, and distance over time is essentially velocity. So we're going to say it's force times velocity. So when you're talking about power output, like when you're swinging a bat or doing a vertical jump, the two components that are related: how much force you're producing and how rapidly you're producing it. Okay, so it's the rate of work being performed. But one of the things we know is that there's an inverse relationship between velocity and force. So what you see here is that at 100% velocity, force is low. But at 100% force, velocity is basically zero. So what happens, if you think about it, say that you could bench press 100 pounds. If you put 35 pounds on the bar, and I say lift as fast as you can lift with a lot of speed. But how much force are you putting into that? Not much. But if I put 100 or 95 pounds on there, how fast are you going to move it? Very slow. Okay? So basically, there's this inverse relationship. So the question is, when is power optimized? Well, power is optimized around 40 to 50, I would say even 40 to 60% of your 1RM. So that's why, like, if you have a baseball player practicing to optimize power, they might train at 40 to 60% of their 1RM to optimize power. So that's the general, what we call power type training. Okay, so basically what we have here is, based on this concept, we have a really interesting concept, which is basically saying that it takes time to reach maximal force. Okay, if you look at this graph, you look at the time to reach peak force, it's about 300 to 400 milliseconds. Now, if it takes 300 or 400 milliseconds, to reach peak force, or 0.3 to 0.4 seconds, you look at a sprint takeoff, 0.08 to 0.1 seconds. A high jump, 0.11 to 0.12 seconds. A shot put, 0.15 to 0.2 seconds. Do any of those reach max force? The answer is no, because it takes 0.3 to 0.4 seconds to reach max force. This means that in sport, we generally don't have time to reach max force. And I can't emphasize that point enough. So basically, let's talk about improving explosive movement. You can train for maximal strength. So if you look at max force on a shot putter, right? About for each arm, they could press maybe about 60 kilograms per arm, okay? Or during a shot put. So max force during a shot put comes out to about 60 kilograms. But if they were to do a maximal press with one arm, it'd be 120 kilograms. So that means that because they're not able to, because it's so rapid, the release, they're only able to get up to 50% of their strength. Okay? So, in other words, yes, what's their max force? 120 kilograms. But they only reach 60 because they don't have enough time to reach 120. We call this the explosive strength deficit. It's called the explosive strength deficit. So, if you have an athlete who's really weak, and they can only bench press, say incline bench press 135 pounds, well, they're pretty weak. If they got their incline bench to 260 pounds, would their shot put go up? Absolutely. Because 50% of that is still going up. But let's say that you start to reach your genetic potential. Say you're incline bench pressing 315 pounds. There's not much more room for improvement in most people there. So how much is strength training going to improve your shot put at that point? Not much. Because it might take a year to add 5 pounds. So the point is, you need to keep lifting heavy to maintain that. The reason why I say that is Dr. Lee Brown makes a really good point. He says that power burns in the flame of strength. You need a strength basis. But once you do that, and you can't get that much stronger, then you need to train for power. And that's the 40 to 60% of your 1RM. When you do that, what you're seeing here is, if you look at the graph to the right, the pre-value is the black, the dark line. You see peak force happens at 300 to 400 milliseconds. When you train for power, peak force is an increase, but notice that you're reaching peak force faster, and that's the dotted line. And that is helping us to overcome the explosive strength deficit. Another thing that we can do to help overcome this concept of explosive strength deficit is we can use a counter movement. So notice pitchers will wind up before they throw. Jumpers will do a squat before they jump, or a counter movement before they jump. Baseball players will wind up before they swing. Hockey players will wind up before they take a slap shot. Why does this work? Well, what I want you to do is take your fingers like you're going to snap. Okay? And snap. Snap. Now, remove your thumb and put your finger in the same spot and slap your thumb down to your hand. Okay? What you're basically hearing is you don't get the same noise because you don't have the same force. But when you actually stopped your finger with your thumb, you had time to build up max force, and that's why you get more of a noise and more force output. When you do a counter movement jump, on the way up, you hit an isometric sticking point, a zero velocity, zero speed sticking point. At that point, you can build up max force before you take off. And that's why counter movements help. So let's move into lever systems. You remember this from kinesiology. What's a lever? Well, a lever basically is comprised of 4 components. You need an axis, a lever system, you need an axis of rotation. Okay? You need a rigid lever, which moves or rotates around the axis of rotation. You need an applied force, which in this case is Atlas pressing down on the lever. You need a resistive force, which in this case is the world. Okay, so again, an axis of rotation, a rigid lever, an applied force, and a resistive force. So you ever hear of mechanical advantage? You know, like for example, when you're using a small wrench and you can't wrench off the bolt, what do? You grab a longer wrench. Well, why does that work? Because you're trying to increase the mechanical advantage. Okay, mechanical advantage is defined by a concept known as the moment arm. Moment arm is the distance between where you apply the force and the axis of rotation. Okay? So, for example, if you look at the boulder all the way to the left, it's 5 centimeters from the axis of rotation. But if you look at where you're applying the force, it's 30 centimeters away. So the moment arm's 30 centimeters on the applied force and only 5 centimeters on the resistive force. That's a 6-to-1 mechanical advantage. You have 6 times the mechanical advantage as the boulder, so it's easier for you. You don't have to apply as much force, and that's important. So first class lever, what happens is that the fulcrum's in the middle, and the resistive force and the applied force are on opposite sides. So in this case, the fulcrum is basically the at the neck, okay, the axo-atlanto joint. So you have essentially that neck, the joint at the neck is center of the neck, and then we have the resistive force, which is your skull, which is bringing you forward, and then you have the muscles at the back of the head, which is the applied force. So first class lever is like a teeter-totter. Second class lever and third class lever, the applied force and resistive force are on the same side of the fulcrum. Okay? But the muscle force has the longer mechanical advantage, or the better mechanical advantage. So, for example, if you look at the applied force on a calf raise, the force is going through the heel. Okay? But if you look at the force when you're doing a calf raise on a machine, the resistive force is more going through the ankle. Okay? So basically there's a longer applied force, a longer moment arm, or greater mechanical advantage for the applied force than resistive force. That's why people can stack out or lift so much more weight on a calf raise. Third class lever is the opposite. The resistive force has a longer moment arm than the applied force. And you can see that here. If you look at the dumbbell in this guy's hand, it's further away than the axis of rotation. Whereas the insertion point on the biceps is much shorter. It means the biceps have to generate much more force than the actual dumbbell. Now, mechanical advantage changes along the range of motion. So if you're doing a bicep curl, for example, mechanical advantage is peaked at around parallel, okay? So 90 degrees of flexion. So this is, for example, why you'll see a lot of people lifting weights and only doing partial reps. Because they have a greater mechanical advantage, they're able to lift more weight, and it makes them feel better. When you're doing legs, your mechanical advantage is best near full extension. So if you go to the gym and you see someone have 4 plates on the bar and they're only squatting 1/4 of the way down, the only reason why they're able to do that is because they have the greatest mechanical advantage. But if they went all the way down when their mechanical advantage was poor, the weight would crush them. So what they're really doing with the short movements is working their ego and not as much their muscles. Now, a good weightlifter understands this. Basically what happens is that they will start off and they'll lift the bar off relatively slowly off the ground. And then when they reach near full closer to full extension, that's when they accelerate really fast and put on as much force as they can because their mechanical advantage is highest. You don't want to be able to exert less forces when your mechanical advantage is highest because your velocity is so high. So you start off relatively slow and then you explode when you're past that halfway point of standing up. You can see that here. Okay? This is where people will apply the most force when they're halfway through that stand-up point, because that way velocity is not as high when they start that point, so force can be higher. Because remember the inverse relationship between force and velocity. You can also use loads to accommodate the strength curve. This is Jordan, for example. He used to be in our lab now. He's a scientist over at Muscle Farm now. And basically you see what Jordan is. As you get stronger along the curve, the chains provide more weight. So this explains why some people are stronger than others. You ever see the guy who looks really lanky but not very muscular, but they go to the bench press and bench 350? It's like, wow, I thought that guy can only bench 150 or 225. Well, if you look at the graph A and graph B, you see insertion points. Who do you think would be able to lift more weight, A or B? Would be B because their insertion points are longer, making their moment arms and therefore mechanical advantage longer. Now, one thing I want to talk about is that when we look at force output, mechanically, force output is produced by the cross-section of the muscle. So if you look at muscle A, it's longer than muscle B, but the cross-sectional area is the same. So muscle B is going to be able to exert the same force as A, but there's less weight on the muscle. That's why if you look at gymnasts, what are gymnasts? They're very short muscles, but what do their muscles look like? Large cross-sectional areas, high force output. Very tall gymnasts might have the same cross-sectional area, but they have more weight on the muscle because it's longer. So this is why gymnasts are so short and stocky. Last concept of the day is strength. We have two types of strength. Absolute strength is basically the maximal amount of weight that I can lift, irrespective of your body weight. And this is going to be important, for example, for linemen and people in heavy weight classes and weightlifters. Then you have relative strength, which essentially is strength over body weight. And this is going to be important for anyone whose body is the implement of interest. So a sprinter, a high jumper, a gymnast, a running back. Those people are going to need high relative strength. But one thing we know is that relative strength, if you look at body weight, and body weight is the open triangles. As body weight goes up, the dark diamonds, that's relative strength goes down. Okay? So basically, as body weight goes up, absolute strength goes up, but relative strength goes down. And that makes sense. Like if you become heavier, it's really hard to do pull-ups. Okay? But you could bench over row a lot more weight. Okay? So this is important because with gymnasts, they actually, if they get too big, their relative strength is going to go down. It's a real good story, basically. If you look at the old USSR, what they would do is they would take their athletes, like their skilled athletes, and before puberty hit, when they had their growth spurt, they'd learn all their technical skills. And when they hit puberty, they'd focus on maintaining skills, but focus on strength and conditioning so they could maintain those skills at an older age when they were larger. So that's the end of the lecture, and I'll see you guys next time.